Hi, Dimitri.
Hi, Ryan.
How's it going? I'm
Nice,
actually
nice to see you
actually I
again.
don't have a webcam today. Family cat was kind enough to bite my screen.
I see.
Hooked up to an external
Well,
monitor.
okay, it happens from time to time. No, everyone's joining, I guess.
Okay, can you hear me?
Yes, I can hear
Okay,
you quite
great.
clear.
So, are you having anyone else join from your end? So, how we're doing this broadcast today? It's actually broadcasting right now over YouTube. So a little past 12 o'clock, I will kick off, do the introduction, and then we'll go from there. I'll monitor YouTube for the questions. After we got Zoom bombed last year badly on two occasions, we have to broadcast via YouTube now.
Awesome.
Yeah, it was not fun.
Yes, you just pair different technologies. Well, at least it shouldn't include any programming, right? It's just settings.
Oh, for Zoom.
Yes.
Yeah, actually, it was interesting because I completely lost control of the session. Um, it was explicit material being popped up, animated icons for profile pictures. It was automated, is all I can say. It was not somebody actually doing that. Okay, there's Bob.
Let's see. Okay. Good morning.
Hey, Bob.
How's it going, Ryan?
Pretty good. We're actually broadcasting right now on Google, on YouTube. So there's a bit of a delay. We got, as I was explaining to Dimitri, we got Zoom bombed last year, or the year before, I can't remember which. So we now broadcast. So the presenter and me we're on Zoom, and then we broadcast out to the group via YouTube.
Oh, I see. So only the three of us will be inside of the Zoom room.
Correct. Yes.
Okay, cool.
It's very private.
And it's to ensure, because I mean, last time I don't know how I thought I had it locked down, and it spiraled out of control pretty quickly. And once it happens, there's no ability to regain control of the meeting.
I see. Ultimately, the link was compromised, so it's out there on Reddit or whatever platform that they were using to.
Yeah, so it was an automated attack. So
I'm sorry to hear
scripted.
that.
Yeah. So yeah, no, I'd heard of Zoom bombing before, but I wasn't really familiar with it.
Yeah, I think that's only in schools.
No.
But no. Yes.
So before we start, Ryan, are you going to be going to DevNexus or anybody from your work?
Not that I'm aware of, no.
Oh no. Okay, well. Which talk are we doing today, Dimitri? Java on ARM?
Yes.
My favorite.
Well, this is a new iteration.
Oh, really? It's
So
different than the one I presented in Vegas?
yeah, because we had that initial material, and now it's a slightly updated view on how things develop for time.
Oh, cool.
Maybe less technical as I see it now, but we can add more details in next iterations.
Brian, quick question. Is the YouTube link on the meetup?
Yes, when they register for it, it should show up.
Okay.
And I hope that fire checkup won't show until we end up.
What's that?
My hotel sent me a note that today there may be a fire checkup. But yeah,
in the heat of the storm?
Yeah, but not earlier than 1 hour from now. So we have time.
So were you able to find the link on Meetup?
Yes, I'm on the meetup. I registered at the Google Calendar.
Yeah, it's a good thing that you're not doing it in person today here.
Is the weather absolutely terrible?
It's snowing,
Oh,
so that would
dear.
definitely impact. We would have had to have
Well,
canceled.
it is good.
Hopefully we can do it in is June a good time in Connecticut, Ryan?
Yeah, generally, yeah.
I think we're gonna do New York, Jersey, and we might do Charlotte again in the June time frame. It'd be awesome to maybe schedule this again. Well, all
Yeah, so yeah, I have to get the venue lined up. That's been the challenge because we lost both of our venues during the pandemic.
Oh, really?
Yeah, so we would meet. We had the venue up in Hartford. I have to check to see what the company that we're meeting with up there got bought out, and then we were being hosted at the Hoberton School in New Haven, and that went under during the pandemic. They had a real nice facility. So I still have to line up a thing. And the commute patterns, at least in Connecticut, I think a lot of people are still working from home.
Uh-huh.
So it's kind of a challenge, I think, because I think the normal patterns of where people would be, because normally we would meet in either downtown New Haven or up in downtown Hartford. And with a lot of people still working from home, I'm not exactly sure how that would impact attendance.
I see. Well, I mean, if we can help out in any way, I'm sure that
Yep.
to some degree, money can find us.
Yeah,
a venue
so
as well.
I'm gonna try to schedule an in-person one, just kind of like a general meetup for those people that are just joining, and an in-person one just to see what we get for people showing up. Because I don't know whether the New Haven one or the Hartford one will get more at the moment.
Question for you. It says, and when the recent public publication is here. I'm trying to see the link got sent to me.
Okay, we're 3 past. I think I'll hand it over now to make Dimitri the host. So just a couple of quick announcements for those people that are joining the stream. I've sent out a link earlier for Oracle has a really basically a conference the day of Java 20's release, the end of this month. So it's virtual or in person, depending upon if you're out in the Bay Area. So Java 20 does come out at the end of this next week, I think. I'm looking to have some type of presentation on Java 20 around that, just to kind of like highlight some of the features. As I mentioned, I'm working on lining up a venue for JUG meetings going forward. So I would appreciate input for those watching from Connecticut as for what location in Connecticut you would prefer and where, because I know that a lot of people are still working from home. So with that, let me make Dimitri the host. For those that aren't aware, Bellsoft is one of the JDK licensees. In addition to Adopt. So let me make host. Okay, Dimitri, you should be the host. Take it away. I'll be monitoring YouTube and also the meetup for questions. So if anyone has questions during the presentation, just post it in there, or even afterwards.
Okay, many thanks, Ryan. You're absolutely correct. We are one of active participants in OpenJDK community, and yes, we means Bellsoft, and I worked in this company for almost 5 years now. Previously, I used to work at Oracle and many other places where my work was related to Java, but not the Java platform itself. But sometime I started to dive deeper into the platform itself. So let's talk about that nice ARM hardware and software running on that hardware that allows us to save some energy, probably to save the world maybe in future, or at least to see some new horizons. So this is a talk inspired by the work that we do for a few years now. And this is the work in OpenJDK project that really it's really an important thing within the entire software ecosystem. And ARM hardware runs that software, which is important. And let's see how they are combined together. Our company delivers its own binary version of OpenJDK called Liberica JDK. That's how we are connected to this space. And of course, we have binaries for ARM, both 32 and 64 versions of it. And we participate in the port development. Besides of OpenJDK builds, we also deliver native image kit builds. That's a downstream distribution of GraalVM Community Edition. And that all helps to keep productions like microservices and other types of productions up to date, secure, running with recent and most performant technologies that we have nowadays. So why am I showing you these outdated iPads and different phones? Well, because we have so many ARM devices on this planet. Just 10 years ago, that was only 30 billion. 30 billion. And now, by this time, it's like older than 250 billion. So that data is for Q3 2022. So I guess now this number it has increased. And the word itself can be read as an acronym with different variants of how it can be spelled. For example, it can be said that it's advanced RISC machines or Acorn RISC machine. And ARM as a company was founded last century in 1985. And there's also a name for the architecture. So what is instruction set architecture? We can look at the definition on the ARM's website. It says that, well, it's a way to connect our programs and the actual hardware. This is the clue. And looking more precisely to different definitions that we can imagine, there's a company that produces that specifications, intellectual property related to that, and it allows different licensees to work with it. There are profiles for ARM architecture, also called ARM in capitals, but the logo you see it's in lowercase letters. And there are different versions or profiles, as I said, of this architecture. We'll see some more of them, but for us, for Java developers and developers of Java itself, so-called application profile is the most important one. Because that's what we expect to get on the hardware that we run our Java virtual machines. And in fact, the architecture allows different modes or states of execution. So you can have a chip and you can switch it. For example, you can do it in Raspberry Pis. You can put it in one or another mode of functioning. And this 64-bit mode is called also it's called AR64. That's the major term here, and it operates or defines A64 instruction set. So there's a set of registers, rules of how what we can expect in that registers, and instructions, of course, that we execute. Our program runs. Surprisingly, there's also an unofficial name, ARM64, which is also used widely. Well, it's still not official, but it's still used widely in projects like Linux kernel. It used to be used in OpenJDK as well. There used to be a port in JDK 8 that was called ARM64. And it was a unified port for ARM64 and ARM32. As I said, there are different licensing options when a vendor decides to build a custom or not so custom ARM hardware. It can be a licensed kernel, or just a license for development, or license for development and production of some reference design for a kernel. And also it depends on what's the type of work. Is it the commercial work or is it scientific work? But it's all interesting, but all work here requires a license. As I said, there are many profiles for ARM hardware. We won't focus on, weaker ones like microcontrollers, but important stages here are ARMv7 and ARMv8, where application profiles are present, and there are just 32 and 64 modes of operation if we look at it in a very simplified way. The hardware may look not so trivial, even from a very top-level perspective. ARM introduced an interesting approach called Big Little, where performant cores are combined with low capability cores. Even in this picture, it's not entirely true, because you see here Cortex X2 and A710. They actually can be inside one system. That are big cores, and they are combined with little cores, and they can have a shared L3 cache. And they actually can have different capabilities, for example, in terms of the modes of operation that they support. And they can be enabled or disabled dynamically during the execution. That actually happens on mobile phones, while on servers it's not the case right now. By the way, I'm not sure about the desktop mode of operation. We'll see one system on chip mentioned today, which may actually work in this mode. I would guess at least it's a relative of such system for sure. Well, if we look at the very simple systems that we are ready to try ourselves immediately, these are of course different toys for toy-like systems when we can do ourselves any programming stuff like Raspberry Pis or other development boards. They are very popular and not so expensive. And the most modern Raspberry Pi, Raspberry Pi 4, which isn't too fresh for now, but still it's nowadays Raspberry Pi 4. It's like a server computer 15 years ago. It's a very powerful machine. And indeed, it's very small. It's a tiny thing that can serve you as a desktop if you wish. It can play videos. It can run very sophisticated code. And on much weaker devices like Raspberry Pi 2 or 3, you can still run OpenJDK, which is great. If you really want something more lightweight or your device doesn't support 64-bit mode of operation, you still can use 32-bit ARM port. It's funny, but it's mainly for now supported by Bellsoft, but it's a big effort because many complex projects are being developed in OpenJDK, and that development requires support from a CPU port side. So within that port, you still can get graphics from your JDK distribution like Liberica, and you can get a very minified runtime using JLink, for example, or using a minimal VM. You can select a minified virtual machine implementation, which will result in a very slim runtime. Of course, you'll lose in performance in that case, but sometimes it's acceptable. You just need sometimes you just need to fit in a very tight frames in terms of size. Meanwhile, ARM 64-bit developed very successfully for more than 10 years. There were multiple notable versions. The major one is number 3 here. So it's ARM 8.2, where we had really interesting capabilities in hardware that or options for having such capabilities that really help big programs, big systems to work with better performance. And also some earlier modifications. I would just spell some acronyms here. Like Neon was inherited from the earlier versions of ISA, and it's a kind of compatible in some sense, or at least it looks very similar. It's a CMD logic that helps you to process, for example, streaming data more effectively. And later, the special vector instructions were introduced. This vector extension is called SVE. And in ARM hardware or ARM specification, sometimes there are optional parts that can be implemented in one or another version of the specification. And also a common practice is for different vendors is to borrow some extensions from more advanced versions of the spec. Of course, different accelerators are very useful, like accelerators for crypto operations or different hashes. And that leads us as for developers to writing specialized versions, of, for example, of intrinsics. We used to cover it in different talks, but so yeah, if you're interested, you can find the descriptions. And sometimes it's tricky, but the main idea is to invoke some specialized instructions in certain cases or implement algorithms using that instructions. And you see now all that, well, 8 versions of specification were successfully developed, and for almost each of them there are known implementations in Silicon. Well, known, I mean widely used or notable, maybe except the last one, I'd say, because at some time a new quality of the spec has developed, and thus ARMv9 appeared with even more advanced vector instructions and also transactional memory support and other many other options. So who licenses that architecture? Well, different companies. I guess all of them are well known to you. And the number is growing because ARM is being used in different devices or special logic boards and whatever. But for us, of course, it's the most interesting part is related to the powerful core designs. And here is the new clear roadmap from ARM itself. The roadmap for development of the so-called Neoverse platform. So the most performant cores. There are a few series of cores targeted to generic purpose server usages and for HPC or high performance computing. So they get new processes for the actual implementation in Silicon. They get new extensions, new versions of the spec, and new designs, reference designs, of course. So that are reference core designs that can be licensed by different vendors, and it really happens. And we'll see some of them. But even before that, before such a roadmap, there were different reference and custom designs. And that's the photo from, I'm not sure, 2018 or 2019, standing with the server, which has 2 CPUs and a lot of cores. It's not being produced right now, but even today it's impressive because it had so many threads in that CPUs. So it's Thunder X2, and it had 256 hardware threads, could address a lot of memory, while still it's not produced because there are other, even more powerful solutions nowadays. At that time, and that's what still continues now, the ecosystem grows and develops. There are many operating systems, not just Linux, but also BSD. And if we talk about Linux, there are different variants of Linux that support ARM hardware. And software for booting ARM hardware and other related things like drivers is being developed as well. And of course, system software and top level applications in the ecosystem, like Nginx, databases, and OpenJDK, of course. The list is continuously being appended, and you can easily check that, or just figure out what happens with your favorite software framework or system. So during that time, we developed a Java enhancement proposal about improving existing or writing new intrinsics for the R64 port. And this is the work that still continues. So we've done some big chunk of this work. And later, it continued in the newer versions of JDK, not just JDK 11, and some parts were backported to JDK 11 updates. Because JDK 11 is still alive, and probably we should not expect any big performance improvements, well, now, but even recently, last year, they were still backported improvements in that version. And then we look at performance, we need some tools. And that tools also work on Linux, for example, on the systems that we are used to. We can use JFR and get some data. It works in R64 port. We can use async profiler or perf and mapping agents. That's the functionality that also works well, and there's no difference from x86 here. And that comes from both sides, from the OpenJDK side and from the side of vendors or supporters of that diagnostic tools. Well, besides of pure performance diagnostic or functional diagnostic, there are also interesting functional aspects. Like ARM behaves differently from TSR architectures in terms of things that we can observe during concurrent execution. So some results here are listed for that processors that could be considered outdated, but this very same happens with all modern CPUs that are powerful enough to perform right hardware optimizations, because this is one of strong sides that helps applications to work better on this architecture. So it means that even when you write Java code, and this test actually works with some Java code, you should be careful, be very precise with your concurrency stuff. Things that don't break on x86 can break on ARM. Not because ARM is wrong, but because the program is wrong. Well, let's get back to different powerful things that we can have. We saw a roadmap, and this roadmap is being implemented in Silicon. And there are different niches for CPUs, like NVIDIA Grace, for example, which is a very powerful processor, or newer AWS Graviton 3, or Alibaba U10, which are custom designs. And you see traditional points here, also they are present. That NVIDIA Grace is a very peculiar thing. It has now up to 144 hardware threads, and it's able to communicate effectively with video cards to accelerate all your computations. So this is a thing for really heavy calculations. And it's a chip implementing ARMv9 specification, while the other one listed here implements Arv8, but that's the first big chip that I know that implemented SV, vector instructions with non-trivial length. And this chip called A64FX powers a big Japanese supercomputer, Fugaku. And there are other supercomputers built on ARM chips. Actually, many of them. This is a rather popular solution. Because supercomputer needs superpower, and building a nuclear plant, copyright, well, sometimes it's not an option. A nuclear plant that will supply power for this supercomputer. Well, if we developed in Java, we unlikely be working with such platforms. Well, we can, but that doesn't sound optimal. And for purposes of application programming, there are server class machines. Like, for example, Ampere Altra family. So this family now consists maybe of 2 chips, and they can be considered as actually a single system, but with some sort of evolution in history. So initially, the CPU supported up to 80 cores. Now they support up to 128 cores. They have good memory bandwidth and other good characteristics. And what's also important, they are freely available for different system makers. So you can buy a server, different servers from different vendors that are built on top of that chips. And they are also used in different clouds. Like they're used in Oracle Cloud, they're used in Azure. So where you can rent some instance in each cloud, or there are multiple types of instances, of course, and they are backed by such chips. Another member of this big family is a chip by AWS. There was a firm called Annapurna, and probably the name still exists somewhere. There are now 3 generations, real generations of that hardware. You see that second generation followed the first generation after 1 year, and third generation followed second generation in 2 years, but actually that are preview dates, and I would say that we saw freely accessible and available Graviton 3 hardware just last year. And you see how this evolution goes here. So the process, how it's being made, was improved dramatically. Clock speed was almost the same, but it slightly increased, because it's hard to have a huge or just bigger clock speed without consuming more power. You see that cores from classical Cortex name became N1 and then V1, just according to that roadmap that we've seen. The number of cores kind of became optimal, right? Some number that you can split into smaller instances or provide as a single bare metal or big virtualized instance. And now Gravitons have greatly increased memory bandwidth. They support new DDR memory standard. They have, of course, more memory controllers than initially, but still it's the same number between second and third generations. But the estimated perf, or we can measure Bogomips or whatever, it's like 10 times more than in the initial version. It's very impressive. And in many presentations, typical generation development is displayed as plus 50 or plus 20% to some characteristic. This is really an impressive velocity in this area. So we can expect even more powerful chips in future. And of course, different cloud vendors have their own strategies about ARM, and probably we should think about Google Cloud. There are only rumors about that, and dates in that rumors are not so close. We'll see. Also, that rumors mention sources of the designs, like that code name Cypress is said to be an in-house design, and that Maple thing is based on some other work. Marvel was named here, but just there's a single source for that information. I can't say is it true or not. Just we look at rumors. But anyway, why is it all happening? What's so special and important? Why is that ARM server hardware so successful? Well, there is a reason. Of course, it helps to save costs, and probably to save costs inside cloud providers, and for them, if they sell it, it can be better profit. At the same time, it will reduce costs for users. So there are a few studies about effectiveness of such chips. For example, here for Graviton 2, Anantech made a comparison, and at the time of that comparison, the chip was extremely effective in terms of cost per operation. And that really means that we can switch our production. In many cases, we can switch our production from our current CPUs to that CPUs offered us by our cloud platform, just changing the name of the instance, and have better performance or have a smaller bill. This is great. And looking at that, vendors, cloud vendors, they collect statistics about usage of ARM platforms in their clouds, and it's growing. So clouds that provide such solutions see their adoption from year to year growing, like from 3% to 7% to 8% now, and they expect it to be 10% next year. And like the last number is from Alibaba, they want to switch more than 20% of their services to ARM by 2025. That's really an impressive growth. And also many vendors report that Java usage on that instances is very popular. So some at least smaller clouds, I saw a number like 80%, which means that it is important to be able to develop for that machines for ARM targets and to debug that and to deploy and run all that we want to run. Well, that's good. But what's about development? Then I touched that big server. We had no good hardware for developers. There were servers, there were small boards that could even power a notebook, and there were some very weak notebooks powered by small ARM chips, but they weren't actually useful. And at some time, that appeared. I like this one especially. You know, there are now even much more powerful MacBooks, Minis, and other Mac computers based on Apple Silicon. But this one is very powerful, and it doesn't need a fan. I really like it. So that's a thing to trade for my money, right? But that's not the only system. So as you know, Macs typically run Mac OS, but there are other machines nowadays. We can run Windows or we can run Linux on them. And it's interesting that Windows runs on tablets, and it's actually Windows that we can use for many purposes. Like in our development process, when we develop OpenJDK and we deliver binaries, when we test, we use such devices. Another interesting machine that appeared last year is a Lenovo powered by a new Qualcomm chip. And that chip is made based on technologies developed in a firm called Nubia that was acquired by Qualcomm. And by the way, they had an interesting dispute with ARM, because ARM said that they are not allowed to build server hardware based on that technologies, because they probably wanted to do it. And by the way, Qualcomm already tried and succeeded in server ARM hardware development. They had a machine called Centriq 200 for 2400 or something. Anyway, that new Gen 3 chip is rather powerful. I won't compare it to M1 or M2, but there probably some comparison that we can imagine. But it is a chip good enough to power not an unusual notebook. So this thing really looks like the notebook that I used to make this presentation. Probably it's more powerful because my one is slightly older, which means this new chip probably outperforms the Intel one in my machine. And it can run Windows or Linux, so you won't notice any difference in user experience. Well, there are for sure a difference in tools that you use, because you must be sure that all the compilers or some other tools that you need that work in this environment. But then we turn back to Java again. There are now 3 ports for different operating systems, but same CPU architecture in OpenJDK. Linux, that existed originally from Java 9. Well, it exists for a long time now. Windows, surprisingly, it came before macOS port and macOS port. And later two were contributed by Microsoft, and they are now backported to JDK 11, and they participated in the projects. We're very glad that there are such ports. And now all vendors use same source of truth to deliver binaries of OpenJDK for that platforms. But besides of basic things like build and provide binaries or test them, there are extra options like working graphics. For example, the JavaFX. And here it depends on the vendor. Like we provide such builds and they work where we provide them. And by the way, we as well provide working graphics in native images. So you can also create a native image, this Wing or JavaFX graphics for macOS on Apple Silicon chips and have good performance, have instant startup, have a single binary, all the advantages of native image. Well, why is it so important to have a native binary or to execute your JVM in a native mode? Because we know that on Apple Silicon hardware, we also have an emulator, and we can actually run x86 JDK there. Well, because it's not that performant. So here is some study where just a bunch of Java benchmarks were executed, and time is measured here, so lower is better. And you see that native execution greatly outperforms the virtualized or emulated one. Well, it's of course a thing that we would expect, but when you see numbers for some of benchmarks, they're really impressive because sometimes difference is more than 2x. So of course it's better to go and get good native builds for your platform, also probably wrapped as a nice installers, but all should work seamlessly. There are many things that require support from a CPU port in OpenJDK. There are, of course, many positive changes that help performance of our legacy applications, and we just can adapt them and get some performance for free. During functional development, you can notice here that ZGC is mentioned, which was imported to JDK 11, but it's available in newer JDKs. As I said, hardware extensions that's there in the new ARM specification implementations help our productions. There's an interesting comparison or measurement of scalability by the link that's listed here. But in OpenJDK, implementing or using that more effective atomic operations. So we'll see here is for outline atomics. It really helps in many cases, and we saw a difference like 5% caused by this support. And it's also backported in JDK 11, which means that we now have much better JDK 11 than it was a few years ago. I mentioned scalable vector extension. And support for using that instructions on CPUs that support it for Vector API has been implemented in third preview in third incubator of Vector API. So it has been integrated in JDK 18. So if you use JDK 18 on you can benefit and you can write experimental algorithms that use Vector API, and they will work effectively on new silicon, like on Graviton 3. Well, for now, from our measurements, so some detour here. Graviton 3 has relatively short vectors, so it's kind of an experimental support in silicon. And it's about the same as using Neon instructions, but in some cases it's slightly faster, which is also the case. So you can already experiment on the real hardware with Vector API and ARM. We saw how many cores such CPUs can have. And besides of having many physical cores and many real carrier threads, we now have an option to execute even much more virtual threads. And virtual threads planning or scheduling requires some support for all specific CPUs that they run on. And virtual threads support, even in preview variants, they support AArch64 hardware, or they are supported in this port. Other important line of development is linked to native functions and native memory. It also supports AArch64, and this is one of the things coming in a newer JDK 20, which will be released next week. So what are our typical daily tasks with our applications? We have all that nice options within JDK. We have our garbage collectors. Things work. We know that runtime does a good job for us. Well, we want to run containers. And running containers is also a normal thing in ARM environment, and it is so for a long time. But we can build that containers in different ways. And still there's no right answer to the question how you should build your containers. Developers do it in different ways. But we must remember that in the end, we use some parent image. We use some image to run our application on production. Well, we also may use some build stack to build our container. And there's a good example where we combine both. It's a way of building containers with Paketo build packs. Unfortunately, build packs for ARM64 are not yet implemented. This is still an open issue. It had dependencies on other projects. Now it's still not implemented. But that's not the only way to build containers from your projects. Of course, it's the most convenient way for Spring, but still you can build jar or native image from your application. And, well, to use some other way to build a container. And during time of JDK 16 development, we delivered a Java enhancement proposal to support Muscle C library that allows to build smallest containers with OpenJDK based on Alpine Linux and other Linuxes that use Muscle C library. And this implementation is not limited to x86. It also supports AR64. So you can really build your container image with on top of one of images with Liberica and Alpine Muscle for ARM64. All the tags are available for that platform. And they are really small containers. So all of the wire, they're all 71 megabytes or less. Either you use JDK or JRE, and they are available for all LTS versions of Java, and of course for newer versions or some intermediate versions as well. And for all that LTS versions, there are 3 critical updates that you can get using the standard means of interaction with Docker Hub. So on top of that, it's so easy to build a container, and here there's no platform dependency. In this example, we just run such a container and ask about CPU information in macOS Apple Silicon environment. And it reports that, yeah, this is some variant of ARM, probably some basic one. And on top of such containers, we can build our containers. It's not as easy as the build packs, because we don't have all that nice scripts that do some work behind the scenes. But we still can estimate our resources, provide some basic parameters, and allow to provide even more parameters from the outside and run the container. And we need a special step if we build a container from x86 environment or in x86 environment for the ARM target, or vice versa, if we build x86 container in ARM environment. We can use cross-build. So Docker now has that BuildX plugin that allow us to specify a target platform. So here, when we are in x86 environment, we know that this Docker file, base or parent image, has multiple variants of target CPU architecture, and our target CPU architecture is supported. And we can build a container using the jar file and Docker file. So it's all possible. In the end, we now have great CPUs. We now have great OpenJDK, and we can combine and use it all in clouds. And cloud providers not just provide us the hardware, they also provide the services that the customer try to sell, or make their environment the most convenient for us users. And that services are able to run on that ARM hardware. Like different managed services, please consult your cloud provider. They can run on their official ARM instances. We have great software ecosystem. We can use modern versions of OpenJDK and have great performance and even better performance each version. And we can even create cross-platform builds for our containers, or use same or different hardware in our development environment. So please send me a message if you disagree, or you want to say thank you, or you just want to meet. It's very easy.
Thank you, Dmitry. It was a great presentation. It's great to hear all the things that are going on with ARM, especially good news on the Apple hardware.
Do we
Just,
have any questions?
yes, there was one question during the presentation, which was what was ST-perf? I
Which
didn't catch
perf?
it in time. Yeah. It was earlier in the presentation, probably before halfway through.
Yeah, some estimated performance. So it's just a metric. No, probably it's here. Yeah, some metrics that different people tried to work out as a single number reference the performance of this chip. So it's one of small lies about performance. You can also calculate Bogla MIPS or request.
Okay.
It's some estimation. I just displayed it here to show well, some approximate, some expectation that we may have about this hardware. We can imagine it's 10 times better than the first generation. That's an impressive improvement.
Yep.
And it's all a combined characteristic of different improvements: memory bandwidth, better single core performance, better caches, all that.
Excellent. Just out of curiosity, with the different ARM processors that are coming out with vendors having, is there anything to look out for in terms of differences between the between the processors?
So there is a big difference between custom design and the reference design. So, for example, I may be beaten here, but behavior of Ampere Altra and Graviton 2 in many circumstances is very similar. I won't say they have exactly the same behavior or exactly the same performance, but the qualitative picture is the same. From another hand, there's Apple Silicon, which is a very powerful beast, and it's a custom design, and they also embed special blocks for this and that, and it really brings great user experience on desktop. So that was a clear intent to have this result. That succeeded.
Years ago, I sat through a presentation on Java, and they were going over how they've optimized Java for different Intel processors at the assembly, with assembly language. They were showing off some of the code for that in the OpenJDK.
Right.
And so with all of these different processors out here, are there differences? Is it Graviton 3? Is there like a code block for certain operations in OpenJDK? To handle something specific for that, or how are they? I mean, back it was simple when there was just Intel and Intel's processors out there. With all of these different processors, is there going to be a explosion of like customizations to try to eke performance out on the different processors, and Java will behave better on one versus another one because somebody did some assembly language or added some optimization for it?
Yeah, thank you. That's a great question. That's my favorite question so far. Because this is a real problem. Yes. There's no, well, there are different answers and all of them are right. Because we can have, and us as developers, we really like to write an implementation that greatly improves some of CPUs. But if we have a really custom implementation for very tiny differences in microarchitecture, first of all, they will blow up the code. and then they will be outdated in a while. So we already seen that for some things that we've made. Sometimes we can simplify code after some time. Sometimes it's just we need to reevaluate, and some sensitive changes that we plan have to be tested on different microarchitectures. So that's an interesting process of finding different chips and running code there.
Yeah, I've been kind of,
Evaluate.
it's just like an
Yeah.
explosion of processors that, we haven't seen in a long time. And I was watching something the other day where they were talking about, I guess early ARM processors, they didn't necessarily include floating point processors. I don't know how far back that goes. But
Yeah,
the performance floating
at
point
least
performance was really bad on some of them.
At least it is simpler for ARM64, but on ARM32, yeah, it's still the case.
Okay.
Yeah. So reviewers in this port in ARM64, they try to keep the code simple, but of course, when if the improvement is significant, well, we still need that.
Is there any chance that we'd see any serious bugs between one processor versus another, or something show up on a processor? You're running an Apple Silicon and you run into some type of timing or race condition bug because it's radically different than another ARM processor, or would you see anything like that?
Well, from time to time, they had such suspicions.
Okay.
But it all turned to be a human error when we code it, just not strictly to specification. So all the hardware that we've seen for the past few years were very stable. We saw some errors in engineering samples, but not now, and not So all very stable. What we do see is that microarchitecture, of course, has great influence on how some exact silicon behaves. So there may be a performance behavior that can be considered as a bug. It is just caused by the design of a processor.
Okay.
Like you may be out of some cache after some normal operations with your application. It can be just large. You can have a lot of code, and that can cause slowdown, not just because the application is big, but because it exceeds some thresholds in units in your CPU, in memory or branches, different ones. And that can cause strange workarounds.
Mm-hmm.
You just do something with your Java application to work around behavior of your CPU.
Okay, great. So I don't see any. See a couple of slides back. Slides on CPU back. Okay, so Todd was saying back a couple of slides on CPU architecture. I'm guessing I was with the SD perf. Okay. So if there's any other questions, just put them in the chat. Otherwise, I think that's it for today. So, oh, wait a minute. Sorry. Jonathan Johnson, does the container from Java app on ARM not work with this JRE? From OpenJDK 17, Alpine, did you recommend another JRE? Let me put that on into Zoom so you can see it.
Yes, if you have the exact text, yeah.
Yep, there we go.
Well, I'm biased here. I recommend Liberica because I know that it works. Probably this one should work too. But, oh yeah, you say OpenJDK. If you go to the description of this container image, you will see that it's deprecated for a long time. Please don't use it for your production systems. That's the short answer.
Okay, so that one has been deprecated for a long time.
Yes.
Okay.
So that was an outcome of the way it was developed previously. So even if you see something called official or just having a short name, it doesn't mean it is a proper choice. For now, yeah, please use Liberica or one of images listed on the page on Docker Hub, this image.
Okay, great. Jonathan says lovely in the YouTube chat. Any other questions? We'll give it a second because there's a delay. If not, and just out of curiosity, the BuildSoft OpenJDK builds, those include JavaFX, right?
Yes, there are multiple flavors. Light, it's a kind of size optimized, and additional backports JDK standard. And there's a JDK version called Full that includes JavaFX as well.
Okay. Great. Thank you. I guess we'll wrap it up. The video, I'll tweak the video online a little bit later, but it will be available on YouTube. So thank you very much, Dimitri. It was an excellent presentation.
Yeah. Thanks for listening.
Thank you. Yep. Thank you. Yep, bye.
All right.